do some smaller sets of data we can really sink our teeth into a bit. Which is not a phrase you're used to hearing. So we want to develop something beyond just the measure of center. Because the whole worksheet showed us, if I just tell you what the average is, it's not good enough. I don't care which average I use, it does not distinguish between different data sets well enough. Are you guys semi with me? Do you all know, by the way, before we get into this, do you all know there is a website, you all know about the website where you can rate your professors, right?
Yeah.
For example.
That's how I found it.
I still remember I worked on the East Coast, and I remember when it first came out. This is back in like 2004 or something, so like back in the before times. The next day, you could tell all my colleagues had gone in and rated themselves. I don't know, do they still have chili peppers or whatever? I don't know. They used to have chili pepper if a teacher was hot. I'm like, okay, whatever. But you could tell they put it in there, and somebody wrote essence of the essence or something. It was just stupid. Anyway, I always tell my students, if I don't get a few bad reviews, I'm not doing a good job. So I'm okay if I don't know where I am. I'm okay if it's down. There's another website that fewer students know about that will tell you grade distributions of every teacher at any school. That is public domain knowledge, by the way. If you call Grossmont and say, I would like to know the grade distributions for the last 6 years of all teachers who taught Math 160, they must give it to you. This is public domain knowledge. Are you with me? You understand? This website, of course, gets it for you, but they charge you money. But if you get in there, it actually has it all plotted out, beautiful little histograms. Are you with me? Everybody understand? So very quickly, if there were two professors, let's say we're at university, what's the main difference between community college and university in terms of grades? Does anyone know? Is D good here?
No.
Why not? Why is it D bad?
It's almost F.
No. D is bad, not just subjectively, but it's objectively
Some
bad.
universities won't accept.
It won't transfer, correct?
Yeah.
Do you know once you're at university and you get a D that actually is a passing grade? You know that. Do you know that?
D's get degrees. Great.
D's get degrees.
I thought it was C.
That applied in high
No.
school. D's get degrees. That applied in high school.
D's get degrees. It's true. Next time you're driving across the bridge, just remember the guy could have got the D in some of his classes. Now,
Same with your dentist.
thankfully, other people check their work. So everybody. So I'm in university. I'm looking at rate my professors. These two people that have exactly the same whatever. I look at this other website for more information, and I find out they both give an average of a C. Everything else about the person, the time the class meets, the kind of person they are, blah, 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 all the same. Are you with me? It's almost freaky, they're clones. Are you with me? Everything else is the same. And I'm like, I need something to tell me which one to take. And I got it, they both give an average of a C. That's not good enough, correct? I need more information. What if one professor gives anywhere from a D to a B, and another professor gives anywhere from an F to an A? Now, if you really think about it, it's dependent on the course. If you know you're going to kick a course's ass, are you going to take the teacher that gives from a D to a B?
No, because you're hurting.
Because you're never going to get an A. Apparently, that teacher never gives an A. Have I ever experienced this? Yes, I have, and I'm still bitter about it. Got the highest grade, and it was B. Okay, I'll be fine. Sorry. So if you know you're going to kick a course's ass, of course you're going to take the teacher that actually gives A's. And if you go to grad school, you will get the teachers that never give A's. They're waiting for like some deity to take it, and then they would get an A minus.
Like that one judge at the Olympics who gives.
You with me? You with me so far? What if you know you're gonna crumble in this class? This is reality. There's classes I took that I knew I was gonna die in, right? And normally they were stuff like painting or something, but I actually did okay with painting, to be honest, but I thought I was gonna die. So if I'm gonna take a class and I'm pretty sure I'm gonna die, I might take the person that doesn't seem to ever fail somebody. Does that make sense?
Yeah.
Okay. Knowing the average is not good enough to get a feel for all the data, and I don't want some giant readout of all the grades. I don't want that shit. I want a summary. The average is a good first step. We all know that's a good first step. Tell me the average, blah, blah, blah. The standard deviation, the spread of the data, how spread out the data is a good second step. Those are the two most important numbers to know about any quantitative set of data. Are you guys at all with me? And it's kind of related to, so the picture, remember the golf balls? Nike, Callaway. Which one had a larger spread? Callaway, right? We didn't talk about it, we didn't analyze it from that perspective, but we could. We could calculate the spread number. Whatever the spread number is, will be smaller for Nike than it would be for Callaway. This is a single number that captures how spread out the data is. So for example, the spread over test grades was 14.3. What the shit does that mean? So to be honest, that's about normal. That is normal. Not normal like this, sorry, but that's expected.
It's more
right?
than a letter grade, isn't it?
Huh?
It's more than a letter grade.
More than a letter grade, sure. Yeah. But it's kind of like that is a normal. Can you imagine from a teacher's perspective, if the spread is too small, what might that mean? Is that good? Did you make a good test if the spread is too small?
No. Not so.
Most likely not, but possibly yeah. If the spread is way too big, that means that some people got 106 and some people got a 17, right? And that's definitely concerning. You with me? So there's a sweet spot for it, but even then, so if I get those two numbers for any set of data, I don't need to see all the damn data. I have a pretty good feel for what the data kind of looks like. Are you at all with me? Okay, so let's formalize what the hell this could be. You're not used to what we're about to do. We are about to construct the equation. We're going to construct the equation and make it tell us what we want to know, right? This is the part of mathematics you guys don't get to see very often. And I often see it as, I'm going to sit the data in a chair, and I'm going to turn the spotlight on, and I'm going to smack it around a little bit and say, tell me. Okay, so we're going to force it to tell us what we want to know. So let me make up some data. Let's say one set of data looks like, what do you got, Jeff? I don't know, Jeff. 2, 3, 3, 3, 4. I like it. And then another set of data looks like 1, 2, 3, 4, 5. Sure. We'll just make it nice. Now, what's the average of both of these sets of data? They both have an average of 3. I like it. Why is that quick to do? Because there's some metric around 3. Do you see that? Yeah, and if you add them all up, you get 3. Okay. So the average for both of these, and I'm going to say these are populations. They're very tiny populations. The average for both of those is 3. Let's formalize what this spread might mean. Does anyone have a feel for which one might be more spread out?
Second one. 2.
Yeah, why do you say that?
The difference between the highest and the lowest number.
Well, okay. So that's why I should have, let me see, how could I change? Oh, let me do this. Do this one change. Here we go. There we go. Because you're right, I want to make sure you understand why the range is not the good second number to use. And we saw this on that, the work you did where everything was 13. Weren't they all the same range? I don't know if you guys remember. I think the range was all 14. If I remember, I can't remember. You guys would know better. All right, I really want you guys to look at it. These both have the same range, exactly. They both have exactly the same mean. Which one is more spread out? Second one. Not because it's got less repeats. So let's formalize what this idea of spread means. If the mean is one number, I want the other number to kind of be related to that. Which, okay, are you ready? Here comes the phrase. Which data set has data numbers that get further away from the average on average? Which data set has numbers that get further away from the mean on average? Second one. Look, doesn't this one have 3 that stay at home if I consider the mean to be home? Mm-hmm. And this one, only 1 stayed at home. Everybody else left. Right? Okay. I feel like somebody's calling on me. Okay. I need something. What's in there? Okay. So if I'm going to analyze this first set of data. So I'm gonna write it like this. This is how we normally write this. 1, 3, 3, 3, 5. Let me ask you this question. If I wanted to know the average, I think I already did this with you, but go with me again. If I wanted to know the average left shoe size of everybody in this room, what would I need to get a list of first? All the left shoe sizes, right? Say that 5 times fast. You with me? If I want to know the average length of a blade of grass in the field on the other side of campus, what would I need a list of?
The average.
Grass blade lengths from that field, correct? I want to know the average distance from the mean to all the data points. So what do I need a list of first?
Well, the distances.
The distance from the mean to all the data points,
From the
right?
average.
Yeah, so I'm going to subtract. So if I take each data point minus the mean, there's going to be an issue, but let's get there. This is a good first step, right? Subtraction is telling me how far apart things are. That's crazy, Jeff. So what do I get here?
-2.
Negative 2.
0,
0, 0, 0.
2.
2. Okay. Now, someday I'm going to do a non-symmetric set of data to really show you, but it doesn't matter if it's symmetric or not. These will always add to 0. There will be equal amounts negative as there are positive. This will always add to 0. Do you guys understand? So right now as you go, thank you, Jeff. Good job, buddy. When you add this shit up, it's always 0. How the hell are we going to get 14.3? It's always going to be 0. Good job. So what's one thing I could do to actually make this more mean distance anyway? What function in algebra means distance? Subtraction is the operation that gives us an idea of distance, but what really means distance? Does anyone know? What function is always positive?
Oh, absolute value.
Absolute value. We're squaring. I like it. You guys all with me? Stay with me. Is everybody with me? I need everybody to understand the problem. No matter what the mean is, no matter what the data looks like, this will always add to 0. Always. Are you with me? Let me do an example on the side. Watch. Give me a number. 2. Give me another number.
7.
7. Give me 2 more numbers. 10, 14. Okay. You guys agree that's not symmetric? Like these are symmetric. You guys agree these are symmetric? You guys see what I mean? What's the mean of these? Somebody help me out. I think that comes out nice. 9, 16. No. Yeah. No. Yes. Is it 8?
10 plus 14. How many numbers is that? 5?
No, it's not 8. Damn it. I was overly. No, it is 8.
It is 8.
It is 8. Yeah. So when I do x minus the mean is 8. All right. This is a side note, right? What do I gotta get?
-6.
Negative 6.
-1, -1, 2.
What do you get when you add these
6,
up?
that's 4. Last one is, oh, sorry. Is it
8 minus 6, or 6 plus 8 is 14.
Sorry.
What do you get when you add these up?
0.
0. You guys with me? I don't care what data you make. I don't care what they are. You can use pi. You can use negative numbers. You can square root of 11. Make up a bunch of data. Take the average. Take the distance. Add them up. You always get 0. That is not helpful. Are you guys understanding? That would make it look like all data sets are the same. They're all 0. Right? Okay. Coming back to our data. One thing I could do, and that we're not going to do, and I'll explain why, is I could take an absolute value of x minus the mean. This is actually something in statistics we do this. It's called the standard error, but you don't see it very often. You see it more often in some sciences. But math people, we always have to be
You
different.
always get a plus or minus absolute value.
No, you don't. No. Nope.
All the time? Oh, okay.
What's the absolute value? 7.
7.
Why?
Just how far?
It's how far from 0 7 is. 7 is 7 steps away from 0. What's the absolute value? Negative 7. 7. Because it's 7 steps away from 0. So absolute value is truly distance. The only number I can take an absolute value of and not get a positive number is 0. Absolute value 0, 0, which is not positive or negative. Are you guys kind of with me? Did you guys know absolute value is based on distance, and that's why the damn thing's always freaking positive? If I said you're negative 4 feet away from me, are you inside you?
No, it's just 4 feet behind you.
No. You would be 4 feet away from me. Distance is positive. I could be thinking about physics, and we're not going to go. So the reason we don't do this, and you don't have to know this, but do any of you know what that looks like if I graphed it?
It's gonna be non-differential. It's gonna be a sharp.
True, that's the actual problem, but I can't say that.
Sorry, it's calc.
What does that look like if I graph it?
Sharp.
It looks like a V. Is that a plane you want to be on?
No.
Thank you for fun. Looks like it's a nice thing. Boom! We are dead. We cannot handle that. You guys with me? So again, this is weird. And again, you pointed out the actual reality has to do with some calculus stuff, even though a couple of things that are above that. But the main reason we don't want to use this is because of this sharp turn. Math doesn't like that. So what's another thing I can do that would take away the negative? I can square things. So what does a square look like?
Parabola.
Now that looks like a plane. Hello, how you doing? Your turn. And we're all fine. We're all fine. Might have banked a bit. We can look down and see some whales in the ocean, right? Okay, maybe. Okay. So again, I really want you to understand the problem. To find the average blank, I get a list of blanks. Fantastic. Makes sense. This will always be 0. Shit. So what I'm going to do is I'm going to square these things, which means at the end, what do I need to do? Because if these are pets people own, this is square pets. Do you understand? And let's not square the fucking pets. So at the end, I got to take
Square root of
square root to undo the squares. Everybody with? So the equation at the end is going to have a big old square root on it to undo the square. So why did we have to square it? To kill the negative. I love it. You guys with me? It's sort of like that song about the little lady swallow fly. You send a dog in. If you guys don't know the song, it's okay. So what do I get here?
4.
That's crazy.
0, 0, 0, 4.
So what I'm about to do, I'm gonna get an average square distance from the mean to all the data points, and then I'm gonna square root that. That's gonna be our standard deviation. So I'm gonna get, how do I take an average anything?
The sigma.
Add them all up, and then divide by the however many there are, right? Okay. So this will be the sum of all of these things divided by how many there are. That is the formula for not the standard deviation, because the standard deviation is going to be at the end when I take a square root.
It's the variance.
This is called the variance. And it's got a nifty little symbol. It's lowercase sigma. Why is it lowercase sigma? Because that's S, and its standard deviation starts with an S. So math people were like, oh, let's use the lowercase. So it looks like a little fat R, I call it affectionately.
N minus 1.
To draw it, you'll see S is N minus 1.
That's an S? No,
That's a Greek S.
Sigma.
Greek letter S.
Sigma.
Greek letter S. Greek. Every civilization can make their letters look like whatever the shit they wanted to. So they wanted a little fat R. Right?
Wait, what is that?
This is lowercase sigma.
Oh.
This is uppercase sigma. The Greek equivalent of the letter S. And of course, equivalencies between alphabets aren't always perfect, but you guys know with me? So to draw this, let's take a second to learn how to draw this. Start at the belly, go around to the cap. Start at the belly, go around to the cap. Sometimes mine are fat, sometimes mine are skinny. It all depends on how I'm feeling at the moment. Okay. Is everybody with me? I really need you to be with me. So the idea of spread being the average distance from the middle to every data point. If that's big, that means the data points get further away on average. If that's small, that means the data points are closer. Hey, that seems like frickin' spread to me, yes? Could it have been a different definition? Yeah. But, too bad for us. They picked it. And it's pretty good. It works really, really well. So, I'm going to stop for a minute. Now again, you never have to fully understand any derivation we do. This is the derivation. Once we get a formula, it's just plug and chug, which I hate, but that's what it is. All right? Here is something key. What am I going to put here? Do I put something there and there?
No.
Because what does this represent?
What you're doing.
Is this any specific number?
That's a variable.
That is all of these numbers. So you can't plug shit in there. Right? You can't put a 1 and a 3 and a 3 and a 3 and a 5. There we go. What the fuck is that? Right? So be careful. We're so used to in algebra replacing every variable with a number. This itself is a number. It's the sum of these. Do I have these?
Yes.
Yes. This is going to happen to us a lot this semester. If I have those, I can add them up. So what number goes on top there?
8.
Oh, should be, sorry, everybody. I got 2 fixated on the symbol. It should still be squared.
64. Wait, no. It's
You guys with me? Because the last thing we can do is take a square root to get the standard deviation. So it's 8.
8.
Yes?
Yeah, it's 8.
With me? What are the sum of these? It doesn't say to square it. It says the sum of these, 8. And what's the total number of numbers?
5.
Holy shit. And what's 8 divided by 5? That's right, kids, 1.6. And then so that is what we call the variance. Before I've taken a square root. So right now, that doesn't mean shit to us. It just means we're not done yet. Later this semester, we'll talk about what that specifically means, how it's used. But right now, I want to get to the spread. So what do I do to both sides?
Square root.
Square root. Square root of 1.6, be careful, it's not 0.4. Don't get overly excited. It's 1 point something. Somebody help me out.
1.264911064.
So about 1.265?
Yeah.
Okay, ready? Big note, big note. We're going to round standard deviation to at least 3 decimal places, always. Can you make it 4? Yeah. Can you make it 7? That's pushing it. Come on. It's got to be at least 3 decimal places, always. Are you with me? I could teach you significant figures, and I don't want to, so we're just going to make that 3. Okay. I could do a lot better than freaking science, I'll tell you that. How many rules? Has anybody ever learned significant figures? How many rules were there?
7.
When I teach it, there's 2. 2 rules. That's all you freaking need, and I'll stop. I'm not going to do it anyway. Okay. So this is a measure of how far each data point gets from the center. Are you guys with me? Yes?
How does what we've derived here differ from, I don't know, let's look at it, I did the homework on it earlier, the sheet, because it's n minus 1 versus just n here.
All right, we're going to talk about
They
that.
mean 2 different
This is a
things.
population. That is the key thing.
I see. Interesting.
So right now, before I talk to you about samples and how it might be different, I want you guys to do everything we just did, but do it for this data set. Can anyone predict anything about this guy's standard deviation number? What did you guys say? It's going to be bigger. Okay, do it. For this data set, yeah. All the exact same work. You need to borrow a calculator. I have some up here too. So you need to still 3. Yeah, I don't know how much battery I've got in there. Oh, sure. Might not be able to record all of today's lecture. Battery.
How many decimals for the deviation?
At least 3. All right, let me catch up to you guys. What goes here?
-2.
Yeah, 1 minus 3.
Negative 1.
2 minus 3.
0.
0, negative 1,
Okay. I like it.
And then the square is
Did you square them to kill the negatives?
410.4.
The formula needs me, so whenever you see a formula that's got this symbol in it, cover it, say, do I have a bunch of those?
Yes.
Yes, so now I can add them up, right?
10.
Yeah, so when you add those up, you get 10, I like it.
Divided by 5 is 2.
2, square root of 2 is?
1.414.
Good. Which is bigger than what we had up here earlier for the first set of data, right?
So the second set is more varied.
Second set has a bigger spread. On average, the data points get further away from the middle. So, very quickly, from a teacher's perspective, how do you say this word? If I got a mean of 71 and a standard deviation of 3, that standard deviation is crazy small. What that normally tells me, especially if we go back and look at all the individual quizzes or tests or whatever, everybody missed the exact same problems because nobody understood those problems. This has happened a few times, right? Do you understand what I'm saying? When the standard deviation is really small, what that normally means is that everybody had some reason to miss basically all the same problems. And that's why their grades were so close to each other. Does that make sense? That is troubling, correct? If the standard deviation was this, that's troubling in a different way, right? That means some people got like 106 or whatever the shit, but some people got 3. You see what I'm saying? So that's way big. So 14 in there is not really a sweet spot. It's just what's most expected. Anyway, that's all I'll say about it. You're not all going to become teachers, so. Okay. All right, so let's take a look at this sheet, because they have a lot more on this sheet. Again, I'll ask if anybody needs this sheet. I mean, need that sheet, you see it? All right. There it is, okay. Gave it out a little while back. Let me know if you need this. Oh, yeah. Anybody else need this? Holy sheet. Who else needed it? Okay, so it's got. Wait a minute. Anybody else need a calculator? Let's do that because we're going to do some calculator stuff. Okay. So you can see this first problem is done for you on this side. But I want to point out a couple things. Oh, that's interesting. You work. What would you say you do here? Oh, you do work. Here, you can have that. Oh. There you go. Thank you. Make sure it's got battery. Yeah, cool. All right, guys. So I asked a bunch of people how many TVs they got. Again, this business. Again, it's symmetric, too bad for me. But same idea, same stuff. But look at the very top. I've given us, if you get a large set of data that you want to do a standard deviation for, I really don't want to do row by row, right? I want something whose entire purpose is to calculate shit, right? What is your purpose? You don't pass butter, you calculate shit for me. So one of the most important points, or buttons in this calculator for us is going to be the stat button. We've already been there before. We've already done into edit. This is when we did like 1-bar stats. So go to edit. If you have stuff in any list, just go up to it and hit clear. Do not hit delete because then your list dies. Poor little dude. Let me know if you need any help. Technology days are always exciting. Okay. So if I put this data in 1, 2, 5, 8, No Jeff. 8, 9. Whoa. Okay. I can go over here. I want the next column to be all the x's minus the mean, but the x's are in list 1. Do you see that? So I want it to be list 1 minus the mean, and the mean is 5. So I want, go up to list 2, highlight list 2, see at the bottom where it's saying, what do you want list 2 to be? And I'm going to tell it I want list 2 to be list 1, second 1, minus 5. Shebang. So, some of you guys might realize, has anybody ever used Excel? Anybody ever used Excel at all? You ever seen it? Okay. If we had enough computer labs, we would teach statistics in computer labs, we would teach statistics on Excel. Because what we're basically doing, Excel does a little better, right? But these are mobile, so hey, what the shit, right? A little trade-off. Because what sucks is if I change this list does not change. I have to recalculate it. Does that make sense? Whereas Excel would kind of update. So then what do I want the next list to be? I just want the next list to be squaring what I just got.
L2 squared.
So if I go to L3, highlight L3, make it equal to L2, shift 2, L2 squared. So look, it's L2 squared. Shabam! Okay. Now this list is not very big. I wouldn't really use a calculator for this list. It's pretty small, but you're going to get bigger lists. So you're going to want to be able to do it in the calculator very quickly. Are you with me? Okay. Feel about it as you will. If I have a very long list of data, I'm like, this calculator costs enough money. Can the damn thing add the numbers up? Please, dear God. I shouldn't have to go 16 plus 9 plus, you know. If I have a very long list of data, it should be able to add the damn data points up. Do you agree? Or you don't care? All right. I'm going to show you. So right now, that is the next thing I need to do. I should talk about that first. The next thing I would do is I would add these up, correct? I would add these up. I want to add up list 3, right? Do you see above stat what it says?
Program or list?
List, yes. So if you hit second mode to quit, get out of your list. Get out of your list. Get back to the nice home screen. Now hit second stat to go to list. You should get this. If you hit second stat, I can do shit to my list now. I want to do math to my list. I want to do the sum of a list. I want to sum up L3. And again, all your lists are above 1, 2, 3. So hit second 3 to get to L3. Enter.
It's like the sum formula in Excel.
Yeah, exactly.
Equals sum, give me the column.
So I'll do it again. So hit second stat to get to list. Because right now I want to do something to a list. I want to do math to a list. I want to sum up the list. So you can either scroll down to it or you can just hit the number 5. You see it? Okay. And then you tell it which list you want to do something to. Yeah. Let me stop for a minute. You guys, again, this is kind of silly to do it on this problem. It's a really small set of data, but still, just to show you how it works. Oh, building out there wants help. Now, before I continue, because let me do it again. What's up?
Do you
So-
have this button that says move? No.
Oh yeah. On the same level as the on button and the stat button, the quit button, stupid important. So say you hit a button, you're like, where the hell am I? Second quit, back home, right? Oh my God. Okay, it's gonna drive me crazy. So let me talk about this real quick. You even try to help me, Martin. You even try to say, why is it N-1? And I always forget. It's tradition.
Oh.
I always forget to explain it before I pass out that thing. So, all the work we did up on the board is related to a population, correct? And people are really confused. Populations don't have to be big. They could be small. They could be very small. They could be a population of 1. That is not impossible. Are you with me? Populations do not have to be large. But what if it was actually a sample I was calculating, and why would there have to be a difference, right? Why should we have to change the formula, Jeff? Don't we have enough formulas? No. We have nowhere near enough formulas. So let me ask you guys this. If I took an average age, if we are the population, and I took an average age, I can then calculate the standard deviation, right? On average, how different is everybody from the average age? Are you guys all with me? Y'all with me? If I took a sample of students, let's say I took this row here, right? You guys are my sample. I just did a very limited cluster sampling, correct? Took everybody from one row. Are you with me? What does standard deviation measure again?
The average
Distance from average.
Yeah, the average distance from the mean to the data points. You with me? If I take a sample and I calculate their average, do you think it's going to be the same as everybody's average? The probability is the same as very low. Do you guys agree with me? Any sample you take, teacher, would put a lot of money on it being different than the population. Are you guys understanding? Their average is not going to be the same as the average of everybody. Do you think these guys' ages will be closer to their average or closer to the average of everybody?
There.
Because I use their ages to calculate their average. They're going to be closer to their average on average. Let me stop for a minute. When I take a sample, if I use the exact same formula, I'm going to get a smaller number than I'm supposed to, because they will naturally be closer to their own average than they would be to the real average. Let me say that again. Any sample I take, the individual data points will be closer to the average of them than they would be to the average of the entire population. Are you guys at all with me? An extreme example would be if they all happen to be really young. Their average would be lower. Their ages would be closer to that than it would be to the whole average, because the whole average would be higher. Are you guys at all with me? Okay. So the fundamental problem is, if I use this exact same formula to figure out the variance for a sample, it's going to be too small. So what we do is, we don't divide by n, we divide by n minus 1. When I divide by less, is the answer bigger or smaller? When I divide by less, the answer is bigger, right? What's 20 divided by 5? 4. What's 20 divided by 4? Yeah, so when I divide by less, the answer is bigger. Are you guys at all with me? So the formula for the standard deviation of a sample is almost exactly the same as this, except two things. So first, this is a population. Oh, there, good. Sure. So this is a population standard deviation. For a sample, the symbol we use is S. Just like, do you remember what was the symbol for a population mean versus a sample mean?
Oh, it's X tilde.
mu versus x bar.
Yeah, mu versus x bar. X tilde was a median.
Oh, sorry.
You're okay. So we chose, I don't know if I told you about the Super Bowl. Super Bowl, back in the day, used to use Roman numerals. Do you guys know that? And you would have these graphics of these, these crazy big rock numerals come, whoa, which is funny because Super Bowl 50 would have just been a big ass L just kind of dropping, right? Why did we use Roman numerals? Because you make it all like, whoa, So here, population, whoa, so population, we use a Greek letter. Sample, we use our letter. Population, standard deviation, variance, we use Greek letter. So for sample standard deviation, we use our letter. actually not our letter. We stole everything. We stole letters and numbers from other people. Right? Our numbers are Hindu Arabic, but you know. So let me start with the variance. The two differences would be, it's not going to be mu, it's going to be x bar, of course, because it's a freaking sample, yes? And I'm going to divide by n minus 1, oops, squared, instead of n. That's the adjustment. It's a sample, that's the adjustment. So then the standard deviation is going to be the square root of all that mess. So it's got one little real difference. I divide by one less. Yeah, I like it. And real quick, I might as well say this whole thing right now.
They're
It's
both
gonna
still
come up
sigma.
later. Huh?
S versus the Roman numeral, they're both still sigma, just one is different than the other.
What do you mean? Sorry.
For sample versus population, on the left of the equal sign, they both still sigma.
Yeah, this is sigma, this is sigma.
The S itself.
What's that? The S?
Yeah.
Over here?
Also sigma?
No, this is S. This is S. Just like x bar is a mean of a sample, mu is the mean of a population, sigma is the standard deviation of a population, S is the standard deviation of a sample. Exactly the same. Okay. You guys enjoy this, I can tell. Okay. So, I want to say one more thing about n minus 1. I love the phrase that just came out of my mouth. Not many people in the world would go, I want to say one more thing about n minus 1. If I had three numbers, and I know they average to be 10, do any of them have to be 10? No. What's the one thing that must be true, though, for them to average to be 10?
Their total divided by 3 must equal 10.
Yes, so the total divided by 3 must be 10. So what must they all add up to be? 30. You guys all with me? If I have any three numbers in the universe that add up to be 30, their average will be 10. Do you understand? So, I could just make up some of the numbers up here. Somebody just give me a random number.
8, 7, 15.
What's the one number, sorry?
8.
8? Okay, somebody else give me a number. 12, sure. How much do I have so far? 20. You could have told me anything. In fact, I was really curious if I get a smart ass that's going to say something like, negative 11 million. Math boy. I would have made the damn thing work, but you know, I want to see if anybody want to give me a challenge.
Okay, do it then.
Like challenge.
Wait.
Negative
Wait.
11 billion, 11 billion, and 30.
That's nice.
May you please do it?
Oh, okay. So what did I say, negative 11 billion?
Yep.
Okay.
No
Well,
way.
all right, let's do this. I want to make sure everybody understands. Okay, so I'll do this one next. All right. So if I make this 8, what do I have so far? 20. And I need
10.
30.
I mean 30, yeah.
Therefore, I need 10. Okay. So when I have three numbers that have to average to something, how much freedom do I have? How many numbers can I just make shit up about? 2 of them, right? N minus 1 degrees of freedom. I have n minus 1 of them that I can just make up. So when I am calculating a sample standard deviation, there's one number I kind of are missing. Do you guys agree if I take a sample, their average is going to be different from everybody else's?
Yeah.
Does everybody agree there is one number I could add to their sum to make it come out to be the same as the average of everybody? Do you all understand? It's just like the frickin' 10 you just told me. There's always one more number I could add to any sample and it would make the average the same. And that's the number we don't know. So that's a more theoretical reason why we divide by n minus 1, because we're pretending like we don't have all n numbers. There's one we don't know. Yeah.
Yeah, the minus 1 represents that.
That unknown, whatever that would be, that would make it the same. Isn't that cool? Some of you guys are like, when is this going to stop? Okay.
Think what this is.
Sorry. So real quick here, that's 10. So I had, you could have made these anything. So what do I make this?
11 and 18.
Yeah, I need this, so it's negative 11 billion. 12. So I need this to be 11 billion. And, sorry, you said it.
18.
18. Beautiful. If I make this 11 billion and 18. These cancel, correct? And then I get 30. So you could tell me any freaking numbers you want to here and here. Could you make it pi? All day long. What about square root of pi? All day long. What about complex numbers? No. Let's keep it real. Keep it real.
Pi wouldn't work so, right? Because you'd have to completely calculate pi in order to account for it.
No. I just subtract pi.
Oh.
Yeah. I'm sorry. I don't know if you guys are still with me. I'm sorry. I went a little crazy. I need you to understand. If I have 3 numbers that average to be something, 2 of them could be whatever the shit I want them to be. That is freedom. Freedom, baby. Right? The third one is going to be the one that makes it what it's supposed to be to have the right average. So how much freedom do I have with n numbers? N minus 1. That's the real idea of what n minus 1 is. Okay. That n minus 1 is going to come up later this semester. And the official name of n minus 1 is degrees of freedom. Yes, I'm going to say it like that. I could take away my calculator. Sorry. So, if you turn this paper over, actually let me point out a couple things. Yeah, board, you're fine. You need to hire a cameraman. Okay.
What it is we don't know is the minus one, but let's take it.
Your minus one is that one number you don't
If I take a sample,
Oh,
if I take a
we
sample,
don't know in the sample.
if I take a sample, you guys, and I calculate your average, you agree with me? It's almost definitely going to be different than the average in the class. There's one ghost student here that I could, if I could add their age, it would make your average the same as the population. That is the one missing number. Do you have to understand everything of what I just said? No, you really don't. This is that the formula is plug and chug, correct? I'm never going to teach that shit that way. I'm going to try to get you to understand the idea of why it makes sense. But at the end of the day, it's plug and chug, right? Are you guys with me? I always want to give my students hope who are like, I don't know what this guy is saying. He's saying shit, words. Yeah?
Is this an example of the formula we would get on a cheat sheet?
Hell yeah. This is going to be like our first real formula. It's going to sit on our formula sheet. I'll call it a cheat sheet. Yeah.
Is another way to think about it, my own brain, it's a way of accounting for, not unknowns, but like variability. It's the variability between that sample's average, the population.
In a way, yeah. So the shortcut I use in my head is the standard deviation formula for a sample, it's adjusted. There's an adjustment because it's just a poor little sample. It can't give me enough information. The n minus 1 is an adjustment. Okay, I like it. Okay. So, I want to point out a couple things. So here we did the work. Blah, 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 blah. Down here, I'm going to ask you a question like this. Oh shit, I've zoomed way in. How many standard deviations from the mean to the data point 2? So I've got the formula here, which is unfortunate, but I will call standard deviation steps. If my data is really spread out really big, I'm going to take big ass steps to get around the data, right? If my data is like stupid small, I'm going to go, right, to get around the data. I don't know if you guys are with me, right? To measure distance between 2 people in this room, would I use miles? No. Could I use miles? Yes.
Sure.
But would I? No. So it makes sense we would use maybe feet, or maybe inches, right? Inches might be the smallest, feet might be the biggest. I want to go, are you guys with me? Yards, maybe I can see. Right? Are you guys with me? If I want to talk about distances between stars, do I want to use inches?
No.
Could you use inches? Yes.
God help you.
Standard deviations are the tick marks on the ruler that I use to see how far apart things are in a set of data. Let me say this again. Standard deviations are the tick marks on a ruler. So when you do a ruler, you can either turn it or it's on the other side where it has like the rest of the world and then us, right? Inches versus centimeters. Are you with me? So the tick marks I choose has to deal with how spread out the stuff is I'm looking at. If I'm talking about stars, are they spread out? Yeah. So then I want my number that I use to measure how far apart things are to be big. We use stuff like parsecs and angular, we talk about degrees of separation between stars. So anyway, I'm not going to teach astronomy. So This idea is using standard deviation to get a measurement. So let me see if you guys are with me on this. If every step I took was 2 feet, and I'm standing at the 11 mark, 11-foot mark, how many steps will it take to get to the 20-foot mark? I want to know exactly how many steps. You can give me an approximate amount, right?
4.5 steps.
Yeah, not too bad. How far do I have to go? How many feet do I have to go? I'm at the 11-foot mark, and I want to get to the 20-foot mark. How far do I have to go?
It's 9 feet total.
9 feet. And every step I take is 2 feet. So how many steps am I going to take? 9 divided by 2, correct? You guys are all with me. All right. Standard deviations are all about the distance from the mean, right? So this idea will always be in relation to the mean. So how many standard deviations from the mean to 2? Well, the data point I'm curious about is 2. The mean is 5, and I divide by how big each step is. That's the calculation we did that was done up here. I'm going to go ahead and tell you the name of this. Some of you guys know this maybe. This is called the z-score. All a z-score is. Okay, this is, let me not say it like that because this is stupid important. Let me say it, let me really give it the build up it needs. Every freaking test I give you from now on, you're going to see one specific question from me. And we're going to talk about the answer right now. Someday I'm going to get more than 50% of the students get it right. Students are always like, tell me what's on the test. And I tell you exactly what it is and what the answer is, and they still get over half the class get it wrong. So you ready? You guys are going to be the first, all right? Here's the door. A z-score tells me how many standard deviations from the mean to a data point. Z-score tells me how many standard deviations from a mean to a data point. You guys with me? Okay. Standard deviation itself is a measurement of how spread out the data is. It's how far, on average, the data gets away from the mean. So it makes sense to use that as a way to measure how far things are. So if you got a really good grade on the test, your z-score might be a z-score of 2. What would a z-score of 2 mean? And we can be very specific now. This kicks ass. I just got excited about numbers, which happens to math people. We know the freaking test standard deviation, don't we? Mm-hmm. So in this case, this is a little bit crazy, but if somebody had a z-score of 2 on the test, can you figure out what grade they got?
Yep. 111.1.
Yeah. Nobody did that, by the way.
I don't think it was
What the shit just happened? What does a z-score tell you? The number of standard deviations from the mean to the data point. So if a student's data point, the student's test grade, was a z-score of 2, that means it's 2 steps, 2 standard deviations above the mean, because it's positive. So what's 2 steps? 28.6, yes? Above the mean. So you add that in.
Sorry, saying above, like, another way would be to the right on a number.
Sure, to the right.
Positive.
Yes.
Negative.
Thank you.
So like with the work done in the sheet, negative 0.85, we took negative 85% of a step.
Exactly. So if a full step, here a full step is 3.5, blah, 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 right? From 2 to 5, it's only 3. It's not a full step, correct? And that's why it makes sense. That's why it makes sense is 0.85 is not a full step. Are you with me? A full step is 3.536, yes? 2 and 5 are less than a full step apart. They're only 3 apart. They're not a full step apart. And why is it negative? Because 2 is below the mean. So a negative z-score means you're below the mean. So for a test, that sucks. For golf or something, that's good, because you want to be below, you want to have a lower score. Are you guys at all with me?
Yeah, so if it was negative 1, your answer would be the exact same. As
Yeah, so if I had a z-score of, if somebody had a z-score of -1 for this test, what grade did they make? -1. How many steps below the mean am I?
60
I'm one step below the mean, correct? It's negative, and I got one of them.
68.
So if you do this minus 14, you get 68.2. Yeah.
F.
D.
Was that a D? Oh,
Yep.
D. What's it? Is F?
Be glad Martin's not great.
F is under 50, yeah. 50 and under would be enough.
60 and under is a F. Yeah.
Because I look at the scores.
Or 59,
I just
yeah.
think of failure.
You guys all
It's a
with
good thing I'm not grading.
you guys at all? Obviously, since this is the most important idea, it's going to be throughout the entire semester. So you got to become more and more and more attuned to what the hell this tries to tell us. But it literally, I tell you, it's just like setting. If I have a very short set of data, very compressed set of data, my tick marks can be really close together. If my data is like really spread out, then I'm going to have much wider tick marks to measure things. Okay, maybe. And then down here, this gets more interesting because, yeah, here we go. If I want to know the percentage of data that's within one step of the mean, one standard deviation of the mean, this is the kind of work I would do. Like take the mean, go up a step, go down a step, and then just count how many data points I just caught. Yes?
What if we were dealing with population for z-score? So it's still.
All the work would be the same.
It would just use.
Yeah. So the z-score for a sample is this one.
Mm.
The z-score for a population is exactly the same, except of course it would look like
Okay.
Greek letters. It's exactly the same idea. Yeah. Okay, maybe. So, I want you guys to do this. And you can work together if you want to. Pull me over if you need. I put up there what to do in the calculator if you want to do it. How much more my calculator, my phone.